you will use different methods to find out variance. So that will give you an idea of how the advantage of different techniques can be made use of to compute variance and to solve other problems also. First, you have got the, we will write out the definition. So this is the actual definition. It's the second central moment, but an equivalent definition is this, which is more useful in computing variance. So we have already computed the expectation of x for the well-known discrete random variables. Now to compute variance of x, we have to find the second moment and then subtract the square of the first moment. So that is the technique that we will normally follow. So first you have got the Bernoulli random variable. So x, it takes two possible values 0 and 1, 1 with the probability and 0 with the probability 1 minus p. So we have already seen that the expectation of x is p. In a similar manner, if you want to find the expectation of y, you will 0, same thing you will find. That's all we get for the. So applying, we will get this is P1 is what we get. So P minus P square is what we get. We can write it as p into 1 minus p, and 1 minus p is what we have been writing as q. So that we can write as p into q. So for the Bernoulli random variables, the variance is p into q. Now the next one is discrete uniform. So we assume that x is uniform between 0 to 1 to n. Therefore, p of x is equal to n plus 1 by 2. That's what we have found. Then we have to just find p of x squared. That is again sigma I ranging from 1 to n. I squared now. That's how the second one is formed. So we have to put this one, I squared into the probability, which is a standard 1 over n. So this is what you have to do. So you have to then put the formula for the I squared one. Will be something like, I am not sure, n plus 1 into 2n plus something divided by some value will come. Okay, that is what the second moment is. And from that we have to subtract the square of the first moment. So this factor, whatever it is depends upon the summation of I squared series minus n plus 1 by 2 the whole square. So 4, and then you do this one, you will get something like, if I remember correctly, n squared minus 1 by 3. You can refer this standard. So that is about the discrete uniform random variable. Then, so again, what we have done in this so far in this two technique is that we have used the standard definition, E of x squared minus E of x the whole square. Then we will find out for the geometric random. So here, what is it actually? Geometric random variable, probability that x equal to k is 2 or k minus 1 into 3. This is what we have to do. The expectation we have found to be a value. What is the value for geometric random variable expectation? 1 by p. 1 by p. It's very easy to interpret that it is inversely proportional to the property of success. Higher the probability of success, on the average you have to do the less number of trials to get the success. Otherwise. Now if you find the second moment, then how is it? Sigma I varying from 1 to infinity, that is the number of trials can range from 1 to infinity all the way, and then I squared into q power I minus 1 into 3, and then you have to do, okay, and then it involves this kind of summations and so on. Sometimes this may be little involved. There are other techniques that we can use. One is, you want to find a quantity, then you can write it in terms of a condition. You use a condition such that when we apply the condition, the quantity is easy to come. Okay. And when the condition is not met, it's difficult, but in a recursive manner you can find out in terms of the same quantity. That is what we are going to do. Suppose the condition that we will try to adopt is x equal to 1. That is in the first trial itself success. There are only two possible ways in which it can occur. X equal to 1 or x greater than 1. These are the two events that can occur. Success in the first trial or success in a trial greater than 1. They are mutually exclusive, collectively exhaustive, and therefore any given statistical quantity can be written as the quantity conditioned on this plus a quantity conditioned on this. This is a general technique that we can always use. So E of x can be written as E of x given that x equal to 1 into the probability that x equal to 1 plus E of x given x is greater than 1 into the probability that x is greater than 1. Note this way of writing is very useful. You are finding E of x. You are computing it given a condition. This is one condition, this is the alternate condition. These are the only two ways by which this can occur, this can be computed. What you have to do is, conditional expectation you have found, then you have to weight it by the probability that the condition is okay. Similarly for this, then you will get this. I will elaborate on conditional PMF, conditional expectation little later, but this should be easy to understand. Now what is this quantity? expectation of x given x equal to 1. That is, the success has occurred in the first trial. Given that, what is the expected number of trials you have to conduct to get the success? It is just 1. So it is just 1. In the probability that x equal to 1, that to get the success for the first time, the probability is p. And this one, given that x is greater than 1, what is the expected number of trials you have? You know that x is greater, for success has not occurred in the first one. Then what is the expectation? Now, success has not occurred in the first trial. So, one trial is wasted. Then you have to wait for the success to occur. But this is an IID random variable, sequence of IID random variables. The number of trials you have conducted, okay, will have no bearing on the remaining number of trials you have to conduct to get this. Clear? Whether you have done 10 trials or all of them have failed, if you ask how many more remaining trials you have to conduct to get this success, it is the same as the original. The probability will not change. So, this is 1 plus E of x. Because 1 is wasted, because the condition tells that it is greater than 1. 1 is wasted. Now, the remaining number of times, the expectation of remaining number of trials, you have to wait to get the success, is E of x itself. Is this understandable? That because 1, it's more than 1, so that 1 is to be included. Then the expected number of trials you have to wait to get the success is still E of x. What is E of x given x greater than 10 is 10 plus E of x. Or it's always, it is Bemelius property, needs to be. And what is this probability? 1 minus p. So we can, E of x can be, look, E of x you don't know, it is, see, E of x of course is 1 of p, but assuming that you don't know, but you can write it in a recursive manner. So it is p plus 1 minus p into 1 plus E of x. So this is p. So 1 is there, minus p is there, and then so I will write 1 plus E of x minus p. So 1 is there. So this E of x, yeah. So what happens is that if this E of x goes away, this 1 comes here, and that will become minus 1 is equal to minus p into E of x. So that E of x is equal to 1 over p. That is what we get again. So that is nothing but this one. But now we will use it for the other one. Same technique. E of x squared is equal to E of x squared given x equal to 1. The probability that x equal to 1 plus E of x squared given x greater than 1 is the probability that x is greater than 1. By about, is this working? When you go ahead, you can check whether these things are working. Yeah, and then once by 25 or so you can keep it. So you can write it like this. So what is again this one? E of x squared given x equal to 1. Okay. So if x equal to 1, it means success has occurred in the first trial. Then what is the expectation of x squared? It is 1 squared into probability x equal to 1 is p. Plus this is always 1 minus p into this quantity E of x squared given x greater than 1. That is, So now x will be 1 plus e of x. The whole square. Sorry, 1 plus x the whole square. Okay, it is yeah, 1 plus e of x the whole square. So this p plus, if you write it 1 plus e plus 1 plus e of x to the yeah, it makes sense because see, given that x is greater than 1, okay, then it is the expectation of 1 plus x now, it becomes 1 plus x. And the whole square you have to do, because you are finding e of x squared, it becomes like this. So it is 1 plus e of x squared will be there, plus this becomes 2x, one expectation, 2 into e of x. And this is plus 1. So then it becomes 1 minus p plus e of x squared into 1 minus p plus 2 into 1 minus p. Okay. So therefore I will take this here. This is 1 minus of here also 1. Yeah, so this is 1. 1 goes away. It's only p. What is this? 1 over p square. So, what do we get? And what is this? 2 by 3. q by t squared is what we get. So that is the advantage of using conditional expectation. The calculation becomes simple. Then we have the Poisson random variable. What is it? If x is Poisson, the parameter lambda, probability that x equal to k is equal to e power minus lambda power k by k factorial for k greater than 0. Integer, yes.
Could you please explain that E1 plus x whole square? Why is it 1 plus EX and why is it E of 1 plus x whole square?
Huh?
In the upper part, why is it 1 plus EX into 1 plus P?
Which one? This one?
EX equal to 1 into P
1 into p.
plus why is it 1 plus EX? It should be EX.
Yeah, because you know the condition is success has not occurred in the first trial. So it is going to occur later. So one trial is definitely there. Remaining, now you after finishing one trial which is not resulted in success, how many more trials you have to wait? The expected number of trials you have to wait to get the success is E of x. Again it is E of x. If you are known that you have wasted and it has not occurred, remaining is again E of x all the time. That is why we are getting it.
And also down there, take 1 square into P plus E of 1 plus x the whole square. The second line. We
Okay.
can explain that second one. How do we get it?
Which one? This one.
Yes.
Again, because it is more than 1, x is greater than 1. What is x? The number of trials you have to wait to get this success. Given that x is greater than 1, it is 1 plus x is the same definition. It is the number of trials you have to wait for to get this. So I can write it as 1 plus x. And as square is what I have to find. So this is what the Poisson is. We have already invoked a binomial expression and told that it will lead to a Poisson expression. Reminding 0 to t and then the lambda into divided by t and all those things. This is the property of success and so on. So what here we are told is if you slice it into a number of ones so that the probability of one event occurring in each one of them, okay, is very small and the number of this one becomes very large, then the Poisson approximation goes. Okay, that is actually a theorem called as the Poisson theorem. So what it tells is, in the limit n tends to infinity and then p tends to 0, but n into p is a fixed quantity. There are two things. One, in a binomial, let us say we have a binomial expression, there is n p. You have a binomial random variable where the number of trials is very large, but the probability of success in each trial is very small. In particular, if n tends to infinity, but p tends to 0, but n into p is a constant. It is not that they are independently, their limits are taken, but the product is a constant. In that case, then what is the binomial probability for k or something proper? N k p over k 1 minus p over n minus for any k. This is the probability that k successes will occur. Then this is approximately given by the Poisson expression itself with lambda equal to n, e power minus np, np power k by k factor. So this Poisson approximation is a good approximation for a binomial expression. when n is large, p is very small, np is a constant. Then you find np and use it as a lambda in Poisson one. You will, whatever you get here, you will get. For example, you have to find, let's say, a probability of success is 0.002 or something like that. You have to do some 10,000 trials, and I am asking what is the probability that 5 successes will occur. Okay? Then you have to use this expression 10,000 5. This 5 can be 50 also, let us say. 50 p power p is 1 minus this one, whatever it is, 0.9 something, power 10,000 minus 50, 99,000 something. So this is not easy to find. Okay. So instead of that, you can invoke it in the Poisson expression, which is much easier. What is the product of this one? This is 20, is it? Huh? So that's it. You can put e power of minus 20, 20 power 50 or 5, whatever you want to compute by 5 factors. So this is much easier. So this is the Poisson expression for this one. So yeah, and no, tell you this I don't want. You can switch on and then click anything. So mn is what? Sigma k varying from 1 to infinity a power n e power of minus lambda lambda power k by k factorial. This is what is the nth moment of the Poisson random variable. Okay. Let me again use this one. So this is the formula for the nth moment. Now to find this one, let's differentiate mn by lambda. So if you do so, what is actually is, this is what we will call it as mn dash. So on this side, what will happen? You are differentiating with this one. You will have minus into e power of minus lambda is the only thing is there. Minus of course, here you can take e power of minus lambda. So if you differentiate with respect to this one, you get this one. And if you want to differentiate with respect to this one, you will have e power of minus lambda. So what you are getting is, this is mn dash, that is different. This itself is mn plus. So now what we will do is, we will divide it by 1 lambda and then multiply it by another lambda. This is k power n plus 1 into lambda power k by k factorial. Clear? So lambda, that becomes lambda power k. Here I have got this one, this remains same, everything remains same. This k power n plus 1 is. So now what is this one? If I suppose leave this lambda, if I take this one, okay, I will take this one. This is nothing but the Poisson probability. And you are multiplying with k power n plus 1 and then doing a summation. What is this one? Mn plus 1. It is the n plus 1th moment. Okay. So it's plus mn plus 1 divided by lambda minus mn is equal to mn. So this is a recursive relation for the moments of Poisson random variable. So we will put we know m1 is equal to lambda. The first moment is lambda. So its derivative is 1. lambda by lambda, okay, is 1, and minus lambda plus m. N plus 1 is what we are looking for. What is that? M2. Everything we are doing for to get M2, the second moment, and then the variance. M2 divided by lambda. So what do we get? 1 plus lambda into lambda equal to M2. So we have got both of them, then we can find the variance. M2, that is lambda plus lambda square, minus M1 square, which is lambda square, that is equal to lambda. So, Poisson random variable, variance of it is also lambda. This is very important. Its mean is also lambda, variance is also lambda. So, we have now given three different techniques. One is find E of x squared directly and then use it to find variance. Another, conditional expectation. Third is give a recursive definition for moment and then you look at a fourth method called so we will get what is called as a moment generating function and then compute moments later. Yeah. Can you switch off the